I'm Nathaniel Eldredge. This talk is Transportation Duality and Functional Inequalities for Markov Kernels. It's joint work with Fabrice Baudouin. So the starting point of this talk is a recent result of Luise-Savaré, which works in what's called an RCDK infinity metric measure space. And what they showed in that setting is that the heat semigroup on such a space satisfies what's called a Wasserstein-Hellinger contraction inequality on the space of probability measures. And I'll tell you what that is in a moment. And so the main result of this talk, or the first one, is that abstractly this inequality is actually equivalent to what's called the reverse Poincare inequality. And in particular, the latter is satisfied in many interesting non-RCD examples. And so this generalizes the previous result and shows that you get this contraction inequality in more general settings. Also, as another result, we modify their approach somewhat to produce a different type of inequality, a so-called entropic contraction inequality. That turns out to be equivalent to, instead of reverse Poincare, the reverse log Sobolev inequality, which we'll also discuss later. Applications of the latter include rates of convergence to equilibrium, or of all of these, include rates of convergence to equilibrium, quasi-invariance, and some other things that we'll discuss. So the setting for the result of Luise-Savaré is a metric space, XD. Should be nice, a complete separable length space. On such a space, you have an upper gradient that just says, given a locally Lipschitz function, look at the difference between the values of x and y, divide by the distance between x and y, and let y go to x, and take the limit sup. So that's why the upper gradient. And if you have a measure on x, you can define the so-called Cheeger energy just by integrating the square gradient of a function. Under certain stronger assumptions, this turns out to actually be a Dirichlet form, and therefore generates a semigroup PT, which is sort of the canonical heat semigroup on the space, and may correspond to be the generator of a nice Brownian motion. So they were interested in spaces that have a so-called RCDK infinity property, which I won't define in detail, but it's based on a Bacry-Emery condition on the so-called iterated Carré-Duchamp of the Cheeger energy. Intuitively, having the RCDK infinity property is telling you that the curvature of x in some sense is bounded below by the number k, which may be positive or negative. So to describe the result, let P of x be the space of probability measures on x, and we'll write mu pt to denote the dual action of the semigroup on the measure mu. And so what they showed is this, that in an RCDK infinity space, if PT is a semigroup generated by the Cheeger energy, that if you look at the Hellinger distance between two measures after being evolved by the semigroup, then that can be controlled by the Kantorovich-Wasserstein distance of between the initial measures. The Hellinger distance is equivalent to, it's a distance for the total variation topology. And so this is telling you something about the total variation between these two measures after the semigroup is applied. And W2 is the usual Kantorovich-Wasserstein distance from optimal transport. In particular, it induces the weak topology, and so it's a much sort of weaker notion of distance. In particular, when k is positive, strictly positive, what this tells you is that the total variation distance between the measures goes to zero exponentially fast as time increases. So you get convergence to equilibrium at an exponential rate. The key ingredient to their proof is that RCDK infinity spaces satisfy the so-called reverse Poincare inequality, which is a statement about the gradient of PTF being controlled by PTF squared, where the constant here is of a certain form in RCDK infinity spaces depending on k. Another key ingredient is that the Wasserstein and Hellinger distances admit what they call a dynamic dual formulation. So for the Wasserstein distance, it says that you can characterize that distance as the sup of the integral of a function phi of space and time. The subscript indicates the time parameter. At a final time with respect to one measure minus the initial time with respect to the other measure, overall phi which satisfy this certain Hamilton-Jacobi type PDE. And this result comes from starting from the so-called Kantorovich duality formulation of the Wasserstein distance and applying the Hopf-Lax formula. There's a similar but simpler characterization of the Hellinger distance. Here you just have an ODE instead of a PDE. And it turns out that actually that using this formulation, then the reverse Poincare inequality implies the Wasserstein-Hellinger contraction quite directly, essentially just because, well, there's a gradient squared here, there's a square of a function here, and the reverse Poincare inequality tells you exactly the relationship between those things. It takes a few more steps, but it's not very complicated. So we were interested in spaces which are not RCD k infinity for any k. So in some sense, they might have no good curvature bounds, not even a negative curvature bound, sort of arbitrarily negative curvature, if you like. But they might still satisfy a reverse Poincare inequality. Some examples might include subelliptic Brownian motion on subrahmanian manifold. This is a degenerate elliptic diffusion. You might want to study semigroups other than the Cheeger energy, even if your metric space is nice. The result only applies if you're using the Cheeger energy. So, for example, you might study semigroups that are non-symmetric or non-local. We were also interested in infinite dimensional spaces where all of these results need to be reformulated a little bit. We discussed this more in our paper. So we showed the following. Again, work in a nice metric space. You don't need a measure now. And you don't actually need a semigroup. It's enough for P to just be a Markov transition kernel. So the time dependence is not important. And then we showed that this reverse Poincare inequality is actually equivalent to a Wasserstein-Hellinger contraction principle like this, where the constant C is the same, up to a factor of 1/4. And so this shows then that, in fact, the reverse Poincare inequality is sort of precisely what you need in order to conclude this Wasserstein-Hellinger contraction principle. And in particular, as noted, statements like this will apply with different constants in a wide variety of non-RCD spaces. Okay, so turning now to another direction, a stronger inequality than reverse Poincare is the so-called reverse log Sobolev inequality. And it looks like this. It's sort of an L1 log L version of what you might think of as the L2 reverse Poincare inequality. We were interested in whether it has a sort of transportation contraction counterpart. And the idea is to use the same dynamic dual type formulation to construct a corresponding transportation distance for which the contraction property might apply. So we did the following. Again, it looks like the soup over some collection of space-time functions of integral phi1 d mu1 minus phi0 d mu0. But now the supremum is taken over all phi satisfying this somewhat different nonlinear PDE that has logs in it, hence the entropic. And it turns out that this gives you not a distance, in fact, because it's not symmetric, but a divergence on the space of probability measures. And in particular, when this A parameter is 0, you recover the so-called Rényi divergence, which is finite only when one measure is absolutely continuous to the other and involves the LQ norm of its density. So something known is encapsulated, something already studied is encapsulated in this. Also, just to show that it's not degenerate, even when A is positive, the distance to a point mass will be finite so long as your measure mu has a square exponential moment. And so we were able to show then that under the same basic assumptions on your metric space, that this reverse log Sobolev inequality is in fact equivalent to an entropic transportation inequality involving this T divergence of the following form. So there's sort of a similar equivalence between these two statements. In particular, in a Riemannian manifold with a lower Ricci curvature bound, the reverse log Sobolev inequality is known to be true. And so then in that case, this transportation inequality is true as well. In our paper, we discussed some other applications that in particular, when you're working on a group, can let you show quasi-invariance properties of the transition densities or the transition measures with respect to translation. And so currently this is only recovering results that are already known, in some sense classical, but we're interested in further applications, possibly to stochastic PDE. This is work in progress. All right. Thank you very much for listening. Here's a link to our EDISR preprint if you are interested in reading more. Here's the paper of Luise-Savaré. I can reach by email. I'll also be online during the discussion session that's scheduled for this conference. And if you look under the poster section, you will find a copy of these slides marked as a poster. Thank you.